So I was talking with James Stillwell the other week, also known as the Open Air Atheist. You can find his channel in the description below. And the topic was determinism, and of course I brought up quantum mechanics as evidence that determinism is incorrect. But James brought up the point that there was also a philosophic reason for determinism, and that my argument from quantum mechanics didn't address that argument. So I want to take some time to address this. And I've seen this argument before by a number of people. Dorpaton had it once, and I saw Thunderfoot argue it a while back. And the argument basically goes that determinism is a natural consequence of the law of identity. So you have A, just some random variable or object, and A has to always equal A, and it can't equal anything other than A. So an object or force has to always equal itself from one moment to the next. Or at the very least, it has to equal an equivalent object or force from one moment to the next. So you have, a cause causes an equivalent effect, causes another equivalent effect down the road, and so on and so forth. Ergo, causality arises from the law of identity and is thus inviolate. So now this looks pretty good, James. The catch is that it's not only the law of identity in play here. If it was just the law of identity here, then yes, causality would have to be absolute. But the catch is that there is a very subtle ingredient added here which is additional to the law of identity that I don't think a lot of people notice when they use this argument. And this ingredient is the idea that time is necessarily an identity operator. Let me explain what I mean by this. So, A equals A preserves identity, right? So you start with A, and then on the other side that just equals A. But now, say you have some function that is dependent on time, and this equals your physical state in one time. The value of that function at that particular point in time will not necessarily have to equal the value of that function at a different point in time. So what this means is that A equals A does not necessarily mean the same thing as cause causes effect. It would be if we assume a certain model of time, but we don't necessarily have to assume that model of time. And, well, the thing is that this is the kind of intuitive model of time, and so therefore it seems as though it's just natural that identity means causality, but it doesn't necessarily have to be the case. So to explain this, I'm going to look at what are called the A and B theories of time. The A theory basically says that we move forward from one moment to the next, and that it's the same nature, and nature always exists in the present. And so this would mean that the flow of time is something that's objective apart from our perception. Now, the B theory of time says that the flow of time is sort of an illusion of our senses, and that time in reality is laid out like a big film strip, and so nature doesn't only exist in the present, there's also the past and the future, and those things are actually really there, they're just not in the present. Now, if you look at the B theory for a moment, you can see why identity doesn't necessarily have to translate into causality. In the B theory, the state of nature in one moment of time isn't necessarily the same thing as the state of nature in another moment of time. A good way to illustrate this would be with a movie film. So you're watching the movie, and time is progressing through it, but it then just suddenly jumps from one scene to the next scene without any seeming causal relation between the two scenes. And so in the B theory, time could actually be laid out like this. You could have, one instant in time, followed by another instant, followed by another instant, but they're all really separate ontological things. And because of this, you can have something in a later moment of time which has no causal precursor in a previous moment of time, in much the same way that, say, a film strip's laid out, and you can jump from scene to scene, and the time was progressing in the previous scene, frame by frame, as though it was each frame caused the next frame. But then suddenly, when you get to the next scene, it just jumps completely as if there was no cause between them. Now, as it turns out, most physicists are actually B theorists. This was largely motivated by relativity, where we discover that time is actually another dimension, not quite like space, but it's in a similar way that space is a dimension. And so you can model time geometrically. You can bend time into space, and if hypothetically, if you bend it far enough, you can create what's called a closed time-like curve, and you can bend your own relative time back on itself. And so, that's time travel, obviously. So the point there is that you're actually going back to the past in that case as though it was, in a sense, a location in space. And that only really makes sense if you view the past and the future as places you can go to, like on the film strip in the movie example. But if the past and the future aren't really there, well, that doesn't really make much sense then, does it? And so because of this, relativity has kind of led a lot of physicists to believe in the B theory of time. Then additionally, there is what's called the Wheeler-DeWitt equation, which describes the wave function of the universe. And this actually, the time-dependent component drops out of this, and so the wave function of the universe, which describes the whole state of the universe, is actually timeless. And so, the universe as a whole would view time as really much like space in a way. And this has led physicists like Julian Barbour to believe that time is an illusion. And he actually uses this to explain precisely what this topic is about, how quantum indeterminism can make sense. And so he actually says that the wave function of the universe defines each instant in time separately, and it just gives you a slightly different value every moment along the way, and because of that, we get things that we can't predict due to quantum uncertainty. And now there is one objection I'm anticipating here, and that is, if you have one moment in time equals one thing, another moment in time equals another thing, then why can't they vary wildly, and why can't we just have, random skips in the timeline with one scene happening and then all of a sudden us finding ourselves somewhere completely different without any explanation for that? In other words, why is there this continuity? Well, the reason for this has to do with the physics of the wave function of the universe. Now, I had a video a while back called Physics of the Hidden World, which was on a Bohmian model of the world, which is non-local hidden variables, which means you're going to get some of your determinism back. It's not going to be local, though. It's going to be kind of spooky action at a distance. You change something here, and it instantaneously changes something somewhere else, but because we can't, we think in local terms, we don't see the determinism there. Anyway, the universe there is described as a big, giant hologram made of quantum wave functions. And the composite wave function that these all make up is the wave function of the whole universe. And this describes the universe at any given point in time. The catch is that we all know that the universe is expanding in time. And at any given point in time, the number of wave functions there are determined by the allowed wavelengths that the size of the universe allows. And so, at one point in time, you'll have a fixed state defined by that, but then as the universe expands, more wavelengths are allowed, but we don't know what the phases of those wavelengths are going to be before they come in, and hence the next point in time is going to have additional quantum waves in it that have phases in them that were not predetermined by what happened at a previous point in time. And so because of that, I think that at least the time-dependent part of the wave function has true indeterminacy in it. But how does this all give us back continuity in time? Well, the answer is that the amount that it changes is very small compared to the amount that it stays the same. And so at our scale, it produces what just looks like normal causality. So I hope this resolves some of your philosophic problems with indeterminism. And that's all for now, guys.